Hello everyone. This is a very special video for me because this is why I started my YouTube channel. I got my idea to start a YouTube channel to explain this information which was available on the internet and in some of the notes of some interesting teachers. And they were teaching chemistry, and there was this formula for stereoisomers which was stated in many of the notes, but there was no explanation which I could find. But then with chemistry, I'm also interested a lot into mathematics and permutation and combination and counting. I like such things, and I tried to derive these expressions, and I was successful. And this is why I started thinking about starting a YouTube channel to let people know about these derivations and many other things. But I never got the time to design this whole presentation. Only after I have already done 60 videos, now I am coming back to the original inspiration for my YouTube channel. So I hope you will enjoy this, and in this video I will be dealing geometrical isomers, and these are the two expressions. You see, there are actually, what is it? What are geometrical isomers, and what do they mean by if like n is even? N is the number of double bonds, and the number of stereoisomers are this and this. So I have already done a lot of videos on stereoisomers, but I will explain about these geometrical isomers from the beginning, and let's start. So we will take some structures and we will start to think how many molecules can we make from these structures. So by structure I only mean connection of atoms. So when I say 1-chloroethene, this is the kind of structure I am looking for. This is your carbon number 1, this is carbon number 2, there is your chloro, and this is 1-chloroethene. Notice I have deliberately not drawn the shape of the molecule because this is just the structure, and when I will draw the shape, then I will start seeing the stereoisomers. So because we know that this carbon is sp2 hybridized, and the shape around this carbon would be trigonal planar, we can think like this. So this is a carbon number 1, this is a carbon number 2, and this is a proper molecule with a shape. And you can think like there's no other possibility. Even if you make a molecule like this, your Cl is here, your H and H are here. You can do certain transformations, and you can superimpose this molecule with this one. You just have to, like rotate it about this axis, then you will get your Cl will be here, H will be here, H will be here, and then take this axis and then turn it, and then you will get this molecule. So with this structure I can draw only one molecule, right? So there is no geometrical isomerism here. So I said that this double bond is not active because for a double bond to be active, both the vinyl carbons, like this carbon here, should have different groups, which it has, and this carbon here should also have different groups. So you will see that your double bond would get active, and it can exist in two configurations, but here it is not happening. And about optically active molecules, it's pretty interesting. You won't see an optically active molecule here with this planar geometry for some obvious reasons, which you can search for. There is a video like what are optically active molecules on my channel. You can go and search for that, and you can watch that, then you can understand. Okay, then now we are thinking about the second structure, which is 1-chloro-prop-1-ene. What kind of structure is this? So because this is prop-ene, 1, this carbon should be 1, this should be 2, this should be 3. This is your main carbon chain, and you have chloro on the first carbon, and 1-chloro-prop-1-ene. So the double bond is at the first carbon. So when you see the structure, you can see that this double bond is active because this and this groups are different, and these groups are different. So when you start to draw the shape, you will find that there are two possibilities. If you keep your CH3 and H here on the second carbon, this is the second carbon, then on the first carbon you can have this Cl very close to CH3 or diagonally opposite. So these are the two ways in which you can draw this these molecules from this structure. Notice the structure is not a molecule, structure is just a structure, and from there you can figure out different stereoisomeric molecules. So you have these two molecules here, and this is now you have got, because you have got one active double bond, your geometrical isomerism has started here. So we have we can say that this configuration, we can decide the periodicity of the groups, which is well understood by these students who are doing stereochemistry. So what you have to do, like take this vinyl carbon and decide which group has higher priority based on the atomic number, and this would be Cl, and here on the second vinyl carbon, this group has the higher priority and they are together, so we call it Z. Z is for zusammen. Zusammen is a German word for together, so this is zusammen, and the higher priority groups are together, that's why this is zusammen. And in the second molecule you see that the higher priorities are opposite to each other, so you use entgegen. Entgegen is the word German for opposite. So these E and Z, they are the configuration of the active double bond, because this double bond is active, as you can see in the structure. It can exist in these two configurations. You should know how to talk about stereochemistry. You need a very good vocabulary to talk about stereochemistry. So now also, what is this one? Because this double bond is at first carbon one, it's on 1 and 2, but we will count the double bond to be at the first carbon. That's why we have written 1Z and 1E. Okay, so let's now summarize this thing. One active double bond, you will get 2 stereoisomers and 0 optically active compounds. Next we go on to the structure 1-chlorobuta-1,3-diene. Let's first make the structure, and you see buta, so 4 carbons, and 1 chloro, 1, 2, 3, 4. So this is the chloro is at 1, and you have 2 double bonds at 1 and 3rd carbon. So this is 1-chlorobutadiene. What do you think? How many active double bonds does it have? So when you're thinking about this double bond, you see on this vinyl carbon, the double bonded carbons are called vinyl carbons actually. So on this vinyl carbon, you have these 2 different groups. On this other vinyl carbon at this double bond, you also have these different groups. You have H here and you have this big group here, okay? So that's why on both the vinyl carbon at this double bond we have different groups. That's why this double bond is active, and at this double bond is also active. It's not active, okay, because you have 2H here. Okay, so this we have 2 double bonds, but only one of them are active. So you can understand that you can make only 2 molecules. You can keep this double bond in 2 configurations, E or Z. This double bond, the configuration of this double bond would not, you can't define configuration here. So we can make these 2 molecules. You see only this double bond at carbon 1 is active, and here you see that the more prior group on this vinyl carbon is Cl, and on this is the bigger group here, which is entgegen. So you have this double bond here in entgegen configuration, and here you have this double bond in the zusammen configuration, as you can see through priorities. So we have these molecules 1E and 1Z. Notice you can't have a configuration at the other double bond. Fine, so you have 1 active double bond again, and you have 2 stereoisomers and 0 optically active, of course. Okay, now let's look at the other structure, 1-chloropenta-1,3-diene. 1-chloropenta-1,3-diene. What happens here is the first carbon, second, third, fourth, fifth. At the first carbon you have this vinyl carbon. At the first double bond you have these 2 different groups here, and at here you also have different groups. So you know now that the double bond at carbon number 1 is active. It can exist in 2 configurations, and this here you have at this vinyl carbon you have an H, and you have this big group, so they are different. And here at this vinyl carbon you have H and this group, so they are also different. So this double bond is also active, and now we have the case of two active double bonds, and the structure is unsymmetric. This is very important. Okay, so when the structure is unsymmetric, what you can do here, I mean, if you will get four molecules, you can understand, because you have two double bonds, right? So these configurations are possible on both the double bonds EE, EZ, ZE, and ZZ. These are the four possible configurations, and four possible combination of configurations. Because this structure is symmetric, the E configuration at one of these double bond, and the E configuration at the other double bond, that's okay, that's a nice molecule. But these two, take a look at this two. You can differentiate this E and Z configuration of the double bonds using their number, and you can't superimpose these two molecules. One might say that, okay, I have EE which is different from ZZ, that I can understand because the double bonds are in different configuration. But here one double bond is in E and one is in Z, and here one double bond is in Z and the other one is in E configuration, but they are structurally different, and that is why these two are different molecules in this case. But in the symmetric case, you can feel that they might superimpose, but we will prove it. So let's see here. We have these four possible molecules, and we can name them according to the configurations of the double bonds, and we can also use the number to represent the which double bond we are talking about. For here, like you have 1E, so this is the first carbon, right? So this is the double bond at carbon number 1. So this is in anti-Gagan configuration, as you can see that the more prior groups are opposite to each other. Okay, so I will also start doing like less prior groups are opposite also, because the more prior groups are opposite. So it's better to look at the less prior group, which is hydrogen, because that would be easier. So take a look at these hydrogens, they are opposite. So the double bond at carbon number 1 is at anti-Gagan. The double bond at carbon number 3 is Zusammen, because these hydrogens are together, as you can see, right? Similarly, you can figure out the rest of these molecules. 1E3Z, 1Z3Z, 1E3E, and 1Z3Z. And if you want to superimpose them, you would not be able to superimpose them. I guarantee you, you can try it. This is pretty basic stereochemistry. But there is one more thing. Let's first summarize it. Two active double bonds, unsymmetric structure, you will get 4 stereoisomers, and 0 of them will be optically active. Of course, I go for optically active molecules also, because in the next video which I am planning about chiral carbons, you will have to understand optical activity also. But here there will be no optically active molecules. Okay, so these are the 4 possible molecules, and suppose somebody comes up with this idea. Take a look at this. Somebody comes up with this pretty interesting idea. They say, why are you making these molecules like this? Because these are sp2 carbons and you have 120-degree bond angles. Why don't you why don't you make it like this? This shape here, this molecule here, also respects the 120-degree bond angle around sp2 carbon. So what is wrong with this? Why is there is no such molecule here, right? It feels like at the first sight, but let's try to figure it out. This is 1Z3Z, right? So the double bond at 1 is at Zusammen configuration. Take a look at this H, and the double bond at 3 is also in Zusammen configuration. Take a look here. And where is your 1Z3Z on this side? This one. But they look entirely different. How the hell we can superimpose these two molecules and say that they are the same molecules? So the idea is like, you see this single bond here. The single bonds can be rotated. They are free to rotate. These double bonds are not free to rotate, right? These double bonds here, rotation is locked because the pi bond will break if you rotate. So there is a big rotation barrier at the double bonds. But the single bonds are sigma bonds and they can freely rotate. So that is the idea. If we use that idea, we would be able to superimpose them. So take a look at this. You have to rotate this single bond and then about this axis, and what will happen now, these green are, these are two directions, so this direction, this green arrow will reach there and this green arrow will reach here. Okay, after 180-degree rotation I will fix this thing, I will hold this thing and rotate it like that. So you can feel it, it will change into, because I am holding this part is as it is, and what happens now, this part, you can see it goes up here, and the edge here, that goes down here. And is it superimposable now? Yes. So that's interesting because because of the geometry around the double bond is trigonal planar, so you have a 120-degree angle, so it's like a trisection of roads. And when you come from here, you have you can also go on this side, you can also go on this side. So when you are making the actual shape of the molecule, you can maybe choose to make it like this, but you just have to look at the configuration of the double bonds to figure out what stereoisomer is it, and you can be pretty sure that there will be only 4 stereoisomers in this case if you have unsymmetric structure and 2 active double bonds. You can try to proceed slowly if it's a little bit tough, but I expect like you have a little bit of idea about geometrical isomerism before, and you were specifically searching for what I explained in the beginning, so I'm building up to that pretty fast. So now we have this another structure, 1,4-dichlorobuta 1,3-diene. Okay, 1,4-dichlorobuta 1,2-diene. This is a buta 1,3-diene, 1 2 3 4, and you have these 2 double bonds here, and both of them are active, as you can see, Cl H on this vinyl carbon, on this vinyl carbon H, and something different similarly on the other vinyl carbon. So this is a case of symmetric structure and 2 active double bonds. What you're gonna do? Well, when you have a symmetric structure, you should have noticed before, like while nomenclature, you can say that this carbon is 1, this is 2, this is 3 or 4, and you can also say that this is 1, this is 2, this is 3, and this is 4, and nothing changes. So there is no unique numbering possible here. That's pretty interesting. That was not the case with unsymmetric molecule structure. But now you have this symmetric structure and you don't have unique numbering. So just like the previous case, we will start by making the 4 possible molecules, and now we can't number them, you just have to think it like it's EZ, ZZ, EE, and ZE. And now this EZ and ZE, they can get superimposed because you can do this movement. Take a look at this ZE molecule, take a look at this axis, and turn this whole molecule about this axis 180 degrees. What will happen? So what will happen? This Cl here will, you see, this is your axis, this is the middle of the molecule where this axis was. This Cl here, it rotates and reaches here, right? And this Cl here, this rotates about this axis and reaches here. And you can similarly figure out the rest of the hydrogens, how they move about the axis. So now you can see that this is this exactly same as the EZ? Oh, it doesn't look like, but it's almost, we are almost there. We need to do one more transformation to make it look exactly like the EZ molecule. But now you can see that this Entech-Again configuration is now at the left side and the Zusammen configuration is at the right side. So it should be superimposable with EZ, but it doesn't look like completely. So you can flip the molecule about this axis or any other axis you want. You can also see some other options, but let's flip this about, let's do a rotation of 180 degrees about this axis. What will happen now? So when you rotate it, let's focus. These 2 hydrogens which are pointing up here, they will start to point down. I'm doing part by part, okay? And this double bond which is here will now go on the upper side and will be visible like this. Your axis is going through this. This is your axis. Let's extend it. So you have flipped the molecule about this axis. First we are looking at this this, okay? Take a good look at it, and then let's build up and let's think about the other part. This hydrogen which is pointing down here is coming here, okay? And then you see this Cl which was pointing down here is coming here, and then you can think about this two chlorine, this which was pointing here is now pointing here, and this hydrogen is now pointing here. And now if you look, they are exactly superimposed. So as we guessed, because there was no unique numbering and the structure was symmetric, we can superimpose Ez and Ze in this case, and this leaves us with only 3 stereoisomers, right? For 2 active double bonds, symmetric case, 2 active double bonds, you will have 3 stereoisomers and 0 optically active, of course. So what has happened with 2 active double bonds? Let's summarize. We get either 4 stereoisomers or 3 stereoisomers. 4 stereoisomers in the unsymmetric structure and 3 stereoisomers in the symmetric structure. And this is like of the format, like you have some numbers to represent where the double bond is, and these numbers are unique because the structure is unsymmetric, and then you have this kind of 4 stereoisomers. And here in this case you can't write a unique number on this double bonds, so you first write these sequences and you figure out that these two are superimposable, and because of that you have only 3 stereoisomers. So this is the basic idea, and we will expand on this, okay? So 3 active double bonds, what can happen? 3 active double bonds, you have unsymmetric or symmetric structure, okay? In the unsymmetric structure, it's obvious that you will get 8 stereoisomers. Why? Because you will have 3 double bonds, and you have you can have Ez, E, Z, 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 these kind of configuration, these kind of combinations of configurations. But how many of them is possible? It's a very simple P and Z question. There are 3 boxes, and in each boxes you can put E or Z. These boxes are unique because they have this particular number XYZ, which is the number of carbon atoms with in the structure. And because of unsymmetric structure, you have these uniqueness here. So you can just think about all the possible 3-lettered sequences with E and Z. So using basic P and Z, you can fill this box in 2 ways, you can fill this box in 2 ways, and you can fill this box in 2 ways. So you will get a total of 8 stereoisomers. If you don't know about what do I mean by filling the box and things like that, you can take a look at these sequences. They're pretty easy to determine. So what I have done here, like with how do I figure out that these are the possible sequences? So let's first think, if you have only 1 double bond, it's either E or Z. If you have 2 double bonds, so starting from E you get Ez or EE and Ez. So I will be writing E first kind of sequences, and then so now starting from Z I can have ZE and ZZ. Okay, so now when I go to 3-lettered sequences, so starting from this EEE, I can go for EEE or EEZ. This is in this format I have written here, right? And now with EZ, so I get EZE and EZZ, right? That's pretty basic. And then from ZE we have these 2 sequences, and from ZZ we have this ZZE and ZZZ sequences, right? So this you can see that how these a number of sequences are getting multiplied by 2 each time we have 1 more active double bonds. And from there you can figure out that there are 8 possible sequences. In the symmetric structure, what is going to happen? You have to look for the non-palindromic sequences. Non-palindromic. What do I mean by non-palindromic? So what is a palindrome? Like this sequence is a palindrome because if you reverse it, EEE, you will get again EEE. So this is a palindrome. But if you see like this sequence EEZ, if you reverse it, you will get ZEE. And because the structure is symmetric, you can feel that if you have a molecule something like this and the structure is symmetric and the double bonds are active, if you and these configurations are, let's say, EEZ. I am just writing without noticing what configuration they are in. If I reverse it, if I rotate it by the middle, by an axis in the middle, then I will get the ZEE molecule. And because this sequence is non-palindromic, what you should do, that you now understand, because of symmetric structure, EEZ is same as ZEE. So you have to look at these non-palindromic sequences which will appear in pairs, and you'll have to cancel one of them, right? So if you start with this palindromic sequence, so that's okay, then you go to EEZ, then you should cut this ZEE, because this combination of configuration is will give you the same molecule as this, because you can flip the molecule from the, like, you can do a 180-degree rotation in the molecule from an axis passing through the middle or anywhere else, to be very frank. Next, EZE, this is the palindrome, so you won't get its the other part of the pair of it. EZZ, this is not a palindrome, so you will get ZZE, and you will cut this ZZE. ZEZ, that's a palindrome, and ZZZ, that's a palindrome, so you're not going to get their pairs, which you will have to cancel. So this EEZ molecule was repeated twice in this total number of sequences, and this EZZ was repeated twice in this list of sequences. And so you cut these extra molecules out, and then you figure out that there will be 6 stereoisomers. So this is the plan. This is very simple. You see, with 3 active double bonds and symmetric structure, this can be done pretty easily. But what if you get more number of active double bonds and symmetric structure? Then that thing gets complicated, and we will generalize. We have the algorithm, we just have to generalize on this. We have to just generalize this algorithm for n carbon atoms. This is what we are going to do. Okay, so 4 active double bonds. Let's try to think about it. Unsymmetric structure and symmetric structure. Take a guess. Unsymmetric structure. So what should we do? We should take all the possible sequences. 16 stereoisomers. You know, X, Y, Z, A, these are the number of carbon atoms where the double bond is, and you have these kind of sequences. How many these sequences are possible? You can understand again using this simple idea. E will give you EEEZ, Z will give you ZEZZ. Then you go to 3 related sequences, you will get 8, and then from beginning from any of these 3 related sequences, you will get 2 more options for 4 related sequences, and this will give you 16 stereoisomers. 16 sequences, and all these sequences you can't flip the molecule in this kind of unsymmetric structure. That's why all these sequences will be representing 1 molecule each, and that's why we have 16 stereoisomers. But in the case of symmetric structure, okay, so this is like, I think you can figure it out how these 16 sequences have been written. It's advisable for you to try it on your own, and just don't believe me, and just try it and write it, and feel that yes, that is correct. Okay, so now in the symmetric case, how many? So we have these possible sequences here, and we will have to figure out how many palindromic and non-palindromic sequences. The first one is a palindromic sequence, right? The second one is a non-palindromic sequence, and its pair is right there, so you will cut that thing out. The third one is non-palindromic, so EZEE, you will find it somewhere, you cut it out. EEZZ, now this is also non-palindromic, cut it out. ZZEE, its pair, cut that thing out. Then again you get EZEZ, non-palindromic, ZEZE, cut that out. EZZE, this is a palindrome, interesting. Okay, so you won't get its pair anywhere. EZZZ, ZZZE, cut it out. Z's, palindromic. Z's, not palindromic, cut its pair out. And all Z, palindromic. So what happens now? You can count. So you can count 1, I mean, like, how many you have cancelled? 1, 2, 3, 4, 5, 6. So 16 minus 6, you have 10 possibilities here. You can also do this idea. You see, P is the number of palindromic sequences. So you take them as a whole, and NP is the number of non-palindromic sequences. You have to take only half of the non-palindromic sequences. That's interesting. So here you can, so this is what I will use in the proof. So here there are 10 stereoisomers, and then now after all this practice, now we can generalize. Now let's start with n active double bonds. What case do we have? Unsymmetric structure and symmetric structure. In the case of unsymmetric structure, how many molecules are possible? Can you guess? Of course, 2 to the power n, right? Because you will have 2 to the power n possible sequences and related sequences, and all of them you will have to, all of them will correlate with a unique different molecule because of unsymmetric structure. But in the case of symmetric structure, you will get lesser number, and in the case of symmetric structure, you will have to divide it into two cases when n is odd and n is even. Why? You will see, because we will the generalization demands this kind of classification here. So what we have done a case of n is odd, like we have done a case of 3 active double bonds in symmetric structure and 4 also. In here we got an answer of 6 stereoisomers, here we got an answer of 10 stereoisomers, but we will have to generalize it. Okay, the idea is very simple. You write down the sequences and you do P plus NP by, whoa, no, sorry, my bad, P plus NP by 2. Now this is wrong. You have to take all of the palindromic sequences and half of the non-palindromic sequences, as we have done before. So what if n is even? You have, how many sequences do we have? I mean, how many boxes do we have? You see, we have n boxes, okay? And in the middle we have these 2 boxes because n is even. And this is, we are indexing these boxes. This is the first box, this is the second box. These are basically, these indexes are representing the first double bond, active double bond, the second active double bond, and things like that. This is n by 2, this is n by 2 plus 1, the index here, right? And then we have to figure out total number of possible sequences with letters E and Z. That's very easy to understand, that it should be 2 to the power n. Because for 3 we got 8, for 4 lettered sequences we got 16, and for 5 lettered sequences will get this number 32. 2 is getting multiplied every time, and this is, you are at 2 to the power at 5. If the length of the sequence is 5, you have 2 to the power 5 sequences. So from there you can understand by induction that it is 2 to the power n. Okay, but the point is, total number of palindromic sequences. How many palindromic sequences are we going to get here? So for that, you just have to think only half of the sequence. For each half sequence of n by 2 length, we get one and only one palindromic sequence. What do I mean? I mean, let's say we are dealing with 6 lettered sequences. If we make a 3 lettered sequences like EEE, then to turn it into a palindrome, if E is here, the last one should be E. If second one is E, the fifth one should be E. And if third one is E, the fourth letter should also be E. So you just have to think like how many 3-lettered sequences you can make, and from each such sequence, for example, let's take another example, EZZ, just fill it backwards and you get a palindrome. So you just have to think about these the half of the length. And how many such sequences do you have? For each of these sequences, you will get one and only one palindromic sequence, right? So that's the idea. So we are thinking just about these, how many sequences of n by 2 length we can make. Of course, 2 to the power n by 2. And from each such sequence, we can make one palindromic sequence of length n. I know it's a little bit condensed video, a lot of information, but verify it on your own. with smaller numbers. So the total number of palindromic sequences we get is 2 to the power n by 2. Let's call it p. So how many non-palindromic sequences? You just have to subtract from the total number of sequences the number of palindromic sequences, and then you get your np. Whoa, and then you get your total number of stereoisomers. P, I'm so sorry for this, you cut this part out, p plus np by 2. Okay, something like this. You take all the palindromic sequences and then half of the non-palindromic sequences. So you get p here and np, this is np by 2. And then you can do a little bit of simplification. So this is this 2 distributes on both of these numbers, and then you get 2 to the power n minus 1, and half of 2 to the power n by 2. You can take 2 to the power n by 2 common, and then you see that this is 1 times 2 to the power n by 2 minus half times these two terms here. They will become plus half times 2 to the power n by 2, and then you've got that expression which is written in a lot of notes, and which can also be found online. And this is that expression for n is even. What if n is odd? N is odd, then in the middle you have just one box, not two boxes. Okay, so then you will have what will be the index of this middle box? So this is interesting, because if you have like 1 2 3 4 5 6 7 boxes, so which one is the middle box? The fourth box, right? And you have 7 boxes, so the half of 7 is 3.5. You will have to add a 0.5 more in to get this index, right? So because n is odd, so it can't be n by 2. It could be either n minus 1 by 2 or n plus 1 by 2. Then if you think properly about it, you will understand that this should be n plus 1 by 2. So this is this index is n minus 1 by 2, 1 less than n plus 1 by 2, and this is 1 more than n plus 1 by 2. Okay, so what happens here? Now you will have to think about total number of possible sequences, 2 to the power n, perfect. Total number of palindromic sequences, then again you will have to think about what? You will have to also consider this central box. Let me give you an example. For example, 3-lettered sequences. How many palindromes did we had? 3-lettered sequences. Okay, so if I think like only this box, and I make a sequence E, and I can make a sequence Z, and what about the middle box? To turn this into a palindrome, you can write an E here. To turn this into a palindrome, you can write a Z here. But what about the middle box? In the middle box, you still have these two options, EZ, E, or E. In the middle box, you can have both of these, Z or ZEZ. In the middle box, you have both these options. So basically, you can you can think like if you have 3-lettered sequences, to make palindromes, just think about these half of the sequence, including the middle box. So you can have EE, EZ, yeah, ZE, and ZZ, and you can turn all of these into one unique palindromic sequence. You just have to write EE. Because there is an E here, you have to write an E here. Because there is an E here, you will have to write an E here. Because there is a Z here, you will have to write a Z here. Because there is a Z here, and you will have to write a Z here. So you have 4 palindromes. Okay, very interesting. So you will have to think about sequences till the middle box, and the middle box is unique here. Okay, and so how many palindromic sequences can we make here? 2 to the power n plus 1 by 2, right? And then how many non-palindromic sequences? Okay, so here I decide, like, if you feel to get a proper feel of it, what is happening. You see, number of palindromic sequences with 2 letters. I mean, like, with E and Z only. Okay, and n is the length of sequence. If n is even, we are getting 2 to the power n by 2, and for n is odd, we are getting 2 to the power n plus 1 by 2. You can revise it, you can go backwards and see that these are the results which we got for number of palindromic sequences. You can verify it. If n is equal to 2, you will get 2 palindromic sequences, and those 2 palindromic sequences are EE and ZZ. If n is equal to 3, you get 4 palindromic sequences, and those are what you have to think, like till 2 boxes you are free to write any letter, and then you can, from there you can make your 4 palindromic sequences. Okay, for n is equal to 4, you get again 4 palindromic sequences. So the even number, like for 4 and for 3, 3 lettered sequences and 4 lettered sequences, you get the same number. And because for n is equal to 4, you just have to think half of the sequence, and those are EE, EZ, ZE and ZZ, and then complete them into palindromes like this. Okay, so this is interesting. You like the odd numbered sequences have, like, they're moving faster in the number of palindromic sequences. They are having a higher percentage of palindromic sequences in the total number of sequences, right? For n is equal to 5, you should get 8. Okay, you can try all of these things out. You can feel this, and then let's now move on to this. So we have this total number of palindromic sequences when n is odd, 2 to the power n plus 1 by 2. Let's call this P. So total number of non-palindromic sequences would be 2 to the power n minus 2 to the power n plus 1 by 2 total minus palindromic sequences. Very simple. And then you use this idea, total number of stereoisomers, P plus NP by 2, as explained before. And do a little bit of calculations, and you get this expression. So these are the 2 expressions for number of geometrical isomers, which we saw in the first minute of the video. You can verify it, but you don't have to memorize this formula, because you have learned something very interesting. You have learned to count palindromes and non-palindromes, and they are not so difficult. Maybe you give this video a repeated watch, and then you will understand why this is so simple. You will have to work it out on your own. Even if I am explaining it, this is of no use to you if you just listen it and you don't do anything about it. I mean, the best kind of viewers would be like stop the video in the middle and say, oh, I got it, and I will figure the rest of these things out myself. But I know that that is not the case for most of you, with most of you, because I have been teaching for a long time, and I see what is happening in the world. Okay, so now let's try to do this question. We are not going to use any formula because this is not so complicated. So let's take a look at the first one. CH3, there is a double bond, This is an oxime, so the double bond of oxime can show geometrical isomerism. That's as a fact you should know. There is a lone pair at nitrogen, so here these two things are different. Sometimes it doesn't happen actually, because there is only one group and one is lone pair. So sometimes the rotation barrier of the double bond could be quite less, and you might not be able to get geometrical isomers in the case of C double bond N. But in this case, as a fact, let's say as a fact, you know that this happens, that this double bond could also be active, and it indeed is active, because on the N side you have a lone pair and OH, on the C side you have H and a very big this group. This double bond is also active, so you have two active double bonds. Structure is symmetric or unsymmetric? Of course, unsymmetric. So you have these unique numbering here. There is unique numbering. Let's say this is 1, 2, 3, 4, and the double bond at carbon number 1 and nitrogen is entirely different from double bond here. So these you can say that this is at carbon 1, this double bond is at carbon 1, and this double bond is at carbon number 2. And actually, like, you might get confused. So because when you have to, like in IUPAC nomenclature, if I want to have this double bond at carbon number 1, I will have to go through it and write a 2 here. But here you see that this double bond is at N. Let's write it N. Forget about 1. So this double bond is at N. So you can say that this is the double bond at N and this is the double bond at carbon number 2. And you can have these 4 sequences, EE, EZ, ZE and ZZ, and all of them will be distinct because of unsymmetric structure, and the answer here should be 4. Okay, how about this B part is pretty interesting, and this question is from this book by M.S. Chauhan, pretty famous book among JEE aspirants, and they have written that there are 2 stereoisomers, but I will show you that this is wrong. It is a case of pseudo-chiral carbon. Geometrically, you can say that there are 2 stereoisomers here, but this I will deal with in the next video. Let's go to this part C. You have this active double bond here, you have this active double bond here, you have this active double bond here. So 3 active double bonds and symmetric structure. So symmetric structure. So you write down all the possible sequences. That's not very difficult to write down. E Z E Z Z. I will show you. This is not so difficult. Don't memorize, guys. And figure out the palindromic ones. These are the palindromic ones. So these are the non-palindromic ones. E Z. So ZEE, cancel this thing out. So this is 1. EZE, this is palindromic. You're not going to find its pair here. EZZ, so ZZE, cancel it out. ZEZ, palindromic. ZZZ, palindromic. 6. We have already done this thing in the video, actually. So you get 6 here. Now here in the last one, you have 1 double bond, 2 double bond, 3 double bond, and all of them are active. You can check, and the structure is unsymmetric. You wouldn't have to cut, you will have to write down all these sequences which we write down here, and you don't cut anything out from there because the structure is unsymmetric, and you get an 8. So 4, 6 and 8 for these options. This one they are saying 2. Why they are saying 2? Because they are looking at this thing like you can think that this ring is planar for these counting the number of stereoisomers purpose, but actually it could be in the chair form, and that wouldn't change things. Actually, that wouldn't change these numbers. That's difficult to explain right here, but I will talk about it in some other video. So what they are thinking here when they are writing 2, because they are counting these geometrical isomers, they are not going for the optical isomers. Here there could be optical isomers also. So what you can do, like you have these 3 methyl groups, and you can understand that these carbons are tetrahedral. So you can have these 3 methyl groups, all of them on the same side, like on the up side of the ring. You can also have all of them on the same side on the down side of the ring. Okay, and you can also have but these two can be superimposed, so they are the same, so you don't count this. And then you can have one ME up and the other 2 down, and actually you see, when you start drawing these kind of molecules, you will get many options, and you will have to check for superimposability and all. And then you will have to figure out how many molecules are possible, how many stereoisomers are possible. But since this question is about geometrical isomerism, rather than writing it all down, which I will do in the next video, which will also talk about chiral carbons. So now I can show you why they're saying 2, because they know that either all the methyl groups will be on the same side, or either one of them will be on the opposite side of the 2 others, right? You have only this kind of options. You have only these 2 kind of options, these 2 kind of options. But what has happened here is that when you take a look at this carbon is chiral because it has all 4 groups different here. This carbon could be chiral. Yes, this carbon is chiral, going to be chiral. because in this molecule there is no plane of symmetry about this carbon. And a lot of things to be discussed about this, but let's discuss it in the other video. This is just about number of stereoisomers in terms of geometrical isomers. So wow, how can I tell you how wrong people are when they are making these kind of questions. So I think I will sum this video up here, and because it's already very long and there was a lot of content, I will talk about this in the next video. Thank you guys.